Okay, if someone could, once again, just give a thumbs up in the chat if they can hear me, just to double check again. Perfect, cool. Okay, thank you guys. So today, basically, I don't know if you saw my message on Canvas, but what my plan is I do kind of have two parts to this worksheet. So the first 6 questions or so are all on the new stuff that we just learned, and hopefully those will be covered in the 50 minutes. I suppose it's possible that goes a little over, but that's my goal for those to be in the original 50 minutes. And then I have about 3 review questions from other stuff we've done this chapter that I'm basically just going to keep having you guys work on until I guess, I don't know, whenever that finishes. So basically you can stay for that part if you want, but you don't have to. So I guess before we get started, I'll also do my chemistry joke. So how much did the dead battery cost? Nothing, it was free of charge. There you go. That's actually one of the better ones, I think, so far. So you're welcome for that. Looking at this first problem then. So basically the new things that we're gonna go over is Gibbs free energy, which we did start covering about a week ago, but I didn't cover any of that in the recitation. So just kind of a little refresher on that. Then mainly electrochemistry, and then one of those redox reactions where you have to balance an acid and base solutions. So those will be what we start going off. Looking at number 1 here, what this wants you to do is basically figure out the Gibbs free energy of a voltaic cell, basically. And so the equation you're going to want to use for this, and I would recommend you have access to this when you take the exam. You should have it if you kept track of Dr. Katz's equation sheet as he went. But basically, the equation you're going to use for this is delta G equals delta G standard plus RT ln Q. And as always, Q, remember, it's the same thing we've always been working with. So it's going to be the products to their coefficient powers over the reactants to their coefficient powers. And so right off the bat, I guess, I'm just going to have you guys get a chance to work this out. You have the equation, you have all of the values you need. So just let me know. One thing you should keep in mind is definitely keep track of the units of these things. So make sure your R value, whatever units that's usually in, is in the same as your delta G standard. And make sure your temperature is in Kelvin, not Celsius. So I'll give you guys, I don't know, as soon as I start seeing some answers come in, I guess I'll move on, but see if you guys can solve for the Gibbs free energy. Guys, just because I don't really know how you guys could send it to me very easily, but basically it's the anode, and we already defined that reduction happens at the cathode and oxidation happens at the anode. So what's going to happen at the anode? We just said this side is the anode, so it's going to involve aluminum and aluminum 3+, but we want the oxidation reaction is going to take place here. So looking, what we have in this table is actually the reduction half reaction. So the only way that you can write the oxidation half reaction is actually just flip it. And so the oxidation half reaction, I'm just going to write oxidation to start with. And what that reaction is going to look like is just this exact same reaction, but backwards. So in this case, it's going to be aluminum solid going to aluminum 3+ plus 3E-. And that's what's happening at the anode. So I didn't actually ask this, but the cathode then is basically just going to be the reduction reaction between nickel 2+ and nickel, which if you look, that's actually what's already given in the table. So what I have that check mark by would be exactly what happens, the reduction reaction that takes place at the cathode, if that were your question as well. But are there any questions on this? Okay, and I would be happy to work through another one of these later. I do kind of want to move on because there are other problems I'm going to work out. Could take a little more time. So this next problem here gives you basically a delta G standard value, and it wants you to figure out what the equilibrium constant is for concentrations. And for this one, I am going to give you the chance to work it out again. Another equation, I guess, I'll give it to you just because it's another thing that you should have on the exam. Make sure you have easy access to this when you take it. But delta G standard is going to equal negative RT ln K. And the reason this works then, if you think about some of the other reactions you're given, or other equations you're given, I guess, what you should remember is that delta G equals delta G standard plus RT ln K. That's just one of the equations you should be given, or ln Q, sorry. And so at equilibrium, remember Q equals K, and you can assume that delta G equals 0. So all you have to do then is rearrange it and solve for delta G standard. So these two equations are related to each other. For this problem though, you just have to use that top equation. So I'll give you guys a few minutes then to work this out. Once again, it shouldn't be too difficult if you have the equation with you, but make sure you know that for this type of problem, you do have to use this equation. But I'll give you guys a few minutes to work that out as well. And so if you're used to rearranging delta H, basically all that means is you're going to plug in, or not plug in, but you find out which direction the reaction's going. If it's going the wrong way, you'll have to add a negative sign to delta H, or in this case to delta G. So if you flip it, you'll put a negative in front of it. If you end up multiplying either reaction by something, you'll also basically multiply K by that value. So looking at this problem then, see if you guys can figure out delta G. Delta S then, basically what you'll have to do for this, delta S, remember, is going to be you have the entropy of the products minus entropy of the reactants. And so that's kind of two parts. As I said, try and work on delta G first, just so I can kind of check your answers, make sure we're on the same page with that. So if you could send me delta G when you get it, and then try working on delta S. So for this next reaction, or problem, I guess, this is when we're going to get into the new redox stuff that we talked about, which actually shouldn't be too difficult, but it does kind of make you think because you really have to break things down and actually think about what's happening. It's a lot more steps than you're probably used to balancing a chemical reaction, but there's a lot less like getting to a point where you have to multiply everything by a lot of stuff just because of how it's set up. And so what I'm going to do actually, and I did kind of leave off the end steps for this, I apologize. What this will give you is the two balanced half reactions. In order to balance the overall reaction, you will have to combine those two reactions and cancel out the electrons. So we will get to that step, but this is a good place to get started. So I guess, I don't know. I will give you guys a chance to get started. If you have no idea how to get started, please message me. And if enough of you start messaging me, I will just kind of go through and explain at least one of the half reactions and let you guys do the other one. But I do think you should be able to at least get started and figure this out. So just balancing that reaction. So as I said, message me if you have no idea where to start, and I'd be happy to kind of just get started with you guys. If not, see if you guys can figure out, I don't know, tell me how many waters are going to be, let's say, yeah, so how many waters you end up forming with this reaction when it's balanced. Okay, so I have a couple correct answers and a couple questions more about how to get started. So I basically am going to kind of just work through, I'll write out the half reactions to start with. And so finding the half reactions, mainly what you have to look at is just see which two species, so one on the reactants, one on the products, actually go together. And so looking at this, it should make sense that zinc and zinc 2 plus go together and BrO3 minus and Br go together, just because one of them is the only one that has zincs, one is the only one that has bromines. So the first half reaction then is going to be zinc to zinc 2 plus. The other half reaction then is going to be bromine, or I don't know, bromate probably. I'm not sure what this is called actually, but BrO3 minus, which is aqueous, going to Br minus, which is aqueous. So this is the first step. So we've defined the half reactions. The second step you're going to have to do then is balance the half reactions for everything except for oxygen and hydrogen. So looking at that, is this balanced as far as by mass goes? The answer is yes. So you have one zinc on the reactants, one zinc on the products. Looking at the other one, remember, it's not is it balanced overall, it's just is it balanced based on everything except for oxygen and hydrogen. In this case, the only thing not bromine, there's one bromine on the reactants, one bromine on the products. So this one is also balanced. So step 2 is actually also complete here. The third step then is to add H2O in order to balance out the oxygens on each side. And so looking at this one might be a little easier than you're used to seeing, just because in this case, the zinc, there's actually no oxygens present either. So step 3 is good for this one. For this one, on the other hand, though, with the bromine, you have 3 oxygens that are reactants. So for every water, you have 1 oxygen. That means we're going to have to add 3 waters to the products. So all we have left then on this side, I guess in this reaction, is we have BrO3 minus. Gives you Br minus plus 3H2O. So looking at that, now everything is balanced except for hydrogens. So we've balanced everything for mass except for oxygen and hydrogen. We've now balanced everything for oxygen. Now what we have to do is for every water we add, we have to add into the other side to make those two things equal each other. Once again, this reaction we actually didn't change at all. So for now, this one is still good. It's balanced for everything except for charge. This reaction, on the other hand, so we have 3 oxygens on each side and 1 bromine on each side. However, the products, we now have 6 hydrogens. So add 6 protons to this side. So 6, 8 plus. We'll go over here. And so now if you look at this reaction, we have 6 hydrogens on this side, 6 hydrogens on this side, 3 oxygens on each side, and 1 on each side. So thinking about then how many electrons you need to add, now what we have to do is actually balance the charge. So for this one, on the reactant side, we have +5 for the hydrogen, or +6, for the hydrogens, -1 for the minus. So an overall charge of this side is going to be +5. The products then, H2O has no charge. We have 1 Br minus with a -1 charge. The overall charge over here is going to be -1. What we have to do then is add electrons to the more positive side to make the two charges equal each other. In this case, the more positive side is the reactants. So in order to make this equal -1, we basically have to do the math of 5 minus how many electrons equals -1. In that case, it's 6 electrons. So that means the overall half reaction is going to be 6 electrons plus 6 protons plus BrO3 minus. Oops. Gives you Br minus plus 3H2O. So that is done. Looking at the other one, this was balanced for everything mass-wise already. However, looking at the charge, this side has a charge of 0. This side has a charge of 2 plus. So what we're going to have to do is add 2 electrons to the more positive side. So this reaction then becomes zinc solid, gives you, zinc 2 plus, aqueous plus 2E minus. And so then the last step that I didn't actually write is you're gonna basically have to combine these reactions to figure out the overall balanced reaction. And to do that, what you look for is the total number of electrons. And basically, however many electrons you have when you add those reactions together has to be the same. So in this case, this reaction has 6 electrons, this one only has 2. So in order to get this to 6, you'll have to multiply this whole reaction by 3. And so we then get 3 zinc solid, gives you 3 zinc 2 plus, plus 6E minus. And so the last step then to write out that overall balanced reaction in acidic solution is you're just gonna add those together. What I'm gonna look at kind of, since this is on the products over here, these electrons, and it's on the reactants over here, I'm just gonna cancel those out to start with. And writing that overall reaction then, we get 3 zinc. And I am gonna leave out the states, I apologize, but just to save some room, and it's a little harder to write the smaller states on my iPad. So we have 3 zincs plus 6H plus Br O3 minus. So that's everything on the reactants of those two reactions, gives you 3 zinc 2 plus Br minus plus 3H2O. And so the answer to the question I asked then would have been 3, because you formed 3 waters here. So the next step is basically, if you've already found the equation balanced in acid, to find it in base is really easy. And in fact, whenever you're balancing a reaction in base, you'll have to do all of these exact same steps. So this doesn't change. You would get to this same point regardless of if it's acid or base. The only step then you have to do is, if it's in a base solution, if you think about it, there's not gonna be extra H pluses floating around. That's something that's present in acid. What you do have is OH minuses. And so what you can think about doing is, every time that you have an H plus and an OH minus that come together, they're gonna form a water. So what you want to do is add an OH minus to each side for every H plus, and you're gonna form waters with wherever there is an H plus. And so how many waters are present now? And I guess I'll have to check. Yeah, so will waters, I guess, be formed, or will waters be used as reactants? So tell me either reactants or products, and tell me how many waters there are this time when this is balanced in base. And I'll just give you guys a few minutes to work that out, and then I'll get started kind of showing you how to do that. Okay, I had a couple correct answers so far, so very nice. Okay, perfect. So quite a few that are saying the right answer. And so basically, as people are telling me, what you do then is, if you add an OH minus for every H plus, since there's 6 H pluses, we're gonna add 6 OH minuses to each side. And so what that is gonna turn into is, we're still gonna have the 3 zinc here. Plus, I'm just right away, for every, since we're adding 6 OH minuses to the 6 H pluses, I'm just gonna write this as 6 H2O. Then plus Br O3 minus gives you 3 zinc 2 plus Br minus plus 3 H2O plus 6 OH minuses. And so this is correct, except what you have to worry about then is actually balancing out the waters and canceling where they're present on both reactants and products. So looking at this, we have 6 waters over here and 3 of them as products. So what you can basically do, cancel out the 3 products and then turn the 6, so subtract 3 from that and turn that into 3 H2O. So I'm not going to rewrite this all again just to save time, but the overall balanced reaction then is going to be 3 zinc plus 3 H2O plus BrO3 minus gives you 3 zinc 2 plus Br minus plus 6 hydroxides. And that should be how you do these problems. And once again, if you have any questions on how to do these later, once I finish the rest of the worksheet, I'd be happy to find another one, maybe a little more challenging on this. But I think as long as you follow these steps, you should be okay on the exam. I could see it ask you to do one in acid and one in base that are separate too. So just remember, if you're ever doing one of these for a base, you're still going to do these exact same first steps. So you'll find how it would balance in acid. But then all you have to do is just for every H plus add OH minuses to both sides, and you should get the correct answer at that point. So just keep that in mind. Make sure when you're balancing that it's careful. I doubt they would give you a really high number of electrons that you'll have to like multiply things by. So just make sure it makes sense how many electrons you're exchanging and things like that. Okay, then I will get to the last problem of the original 6, I guess. And this one is kind of a little more review from last week as well. So this there's a couple different ways to work this out. And so this goes back to the delta G equation, where basically the definition of delta G is that delta G equals delta H minus T delta S. And so the question is the reaction ever spontaneous? And if so, above or below what temperature? And so I will give you guys all a chance to work that out. And once again, message me when you get your answer. And this one is kind of a trick question in a way, I guess, but you should still be able to figure it out. All the answers I've gotten so far are correct, so nice job. Okay, I'll give you guys about, I don't know, 30 more seconds to a minute left. All right, so most of you got this correct, but basically, so there are kind of two ways to go about this. What you can think about, first of all, so I'll just do the math to start with. So let's say we plug these values in. Notice delta S is in joules, not kilojoules. So we're going to get here then is that delta G equals 301 kilojoules per mole minus T times negative 0.190 kilojoules per mole. Just converted that into kilojoules there. per mole Kelvin, sorry. So this is what you're solving for T for then, and that is a T, I apologize. So looking for this, when it becomes spontaneous, remember, that's when it's going to equal 0, is going to be that point. And so that point where it equals 0 is basically going to solve for when this equals 0. And what you should get if you solve for T then is that you get T equals, I think, negative 1584.2. Now, inherently, if you think about it, using the Kelvin scale, you cannot have a negative number. And so what this tells you is that in order for it to start becoming spontaneous, it has to be basically, in this case, greater than negative 1,500, or sorry, for it to be spontaneous, it has to be less than negative 1,584.2 degrees. Obviously, it can't do that. So this means that it's going to be non-spontaneous always. So if you ever solve for this and get a negative number, you know that it's basically going to be, it's never going to be spontaneous. The other way you could think about this is think back to that one table where you were given if like delta H is positive, delta S is negative. If delta H is positive and delta S is negative, it's always going to be non-spontaneous too. So just make sure you have that table handy when you take the exam as well. That's the one that I think it's in your Reci manual, and I don't really have an easy way to show you the actual table right now just because I don't have a dot cam or anything to show the Reci manual, but that's where you have like delta H, delta S, and like you have positive, negative, positive, positive, and so on, and it tells you whether it's spontaneous or not. Make sure you have that handy because that could actually save you some time on something like this if it ended up being non-spontaneous all the time. The odds are if they ask something like this, they won't actually trick you. So if they ask above or below what temperature, my guess is it will be a real temperature. But I do think they're also going to ask you questions about whether, like predicting whether something is spontaneous or like whether it's always spontaneous or not. So this kind of just threw those two things together. And so, as I said, I guess we finished a little early. Those are the first 6 questions that I was going to do that are kind of newer stuff. I am going to keep moving on then to 7, 8, and 9, and I don't know how long this will take, but it will definitely run over time. So feel free to stick around or feel free to head out if you're good with the review. But I am going to move on now to this extra part. And yeah, so someone just asked in the chat. So it is never spontaneous. Did want to clarify. So never spontaneous because the temperature is negative when you find it. And you can't ever have a negative temperature in Kelvin. So that's a good indicator that it's never going to be spontaneous. Or as I said, the other way you could do this is by looking at that table and knowing that if you ever have enthalpy is positive, entropy is negative, delta G can never be spontaneous. So those are the 2 ways that you could go about doing this. If you did it that other way, you wouldn't even have to do the math. But if you end up doing the math and you solve and get a negative value, that means it was also never able to be spontaneous. Good questions. So moving on then, this one is an entropy question. And so thinking about entropy of the universe, remember this all comes down to delta S of the universe equals delta S of the system minus delta S, or sorry, plus delta S of the surroundings. And so the equations you're going to want to use then for delta S system and delta S surroundings, remember, our delta S of the system is going to equal delta H of the system over temperature of the system, delta S of surroundings equals negative delta H of the system over T of the surroundings. So I will give you guys a chance to work with what I've given you there, see if you can figure out what delta S of the universe is. And yeah, if you have any questions or don't know where to get started, once again, feel free to message you and I can either reply in the chat, or if it's more complicated, I guess just explain it to everyone. So yeah. And the values you get here, since I didn't specify an amount of water, you are going to get a unit and it's going to be per mole. If it were ever to ask you something about like finding the actual entropy or enthalpy for a certain mass, you would do the exact same steps, except you would then multiply whatever you get times however many moles you have, in this case of water, and that would give you an answer that's like for that specific value. Gotten a couple correct answers and they've all been correct so far. One thing I would be careful for this though, you should get your answer for this since I didn't specify a number of moles or a mass. You'll actually get either kilojoules per mole Kelvin or joules per mole Kelvin as your units. So just make sure that that moles is in there. And that way, if you think about it, just how things are going to end up canceling out, that would make it so you'd end up having, if you had a certain mass, it would give you the correct units for that mass. And I will say, if you're in kilojoules, it's going to be a really small number. If you convert to joules, it'll make a little more sense. Okay, I'll wait for one or two more people to send me what they get. And for delta S of the universe, remember what, if that's positive or negative, what that actually ends up meaning. Okay, so thinking about it, some of you are getting it right, some are off by a little bit. But all you're gonna have to do for this then, so delta H of the system is basically also going to equal, in this case, delta H of vaporization. So whatever the process is happening, that is the delta H that goes with it. So in this case, delta H of the system is just going to equal 75.3 kilojoules per mole. This is where you have to think about then, so T of the system versus T of the surroundings. So because water always vaporizes at 100 degrees Celsius, we can assume, and I guess it's given here as well, that the water is vaporizing at this 100 degrees Celsius value. So that's going to be the T of the system when this takes place. Thinking about, so when I say it's vaporizing at its boiling point, that means that when it's vaporizing, it's going to actually be, so the temperature of the water is going to be 100 degrees Celsius. The surroundings in this case then are going to be 68.9 degrees Celsius. So looking at that then, just using these two equations, delta S of the system. So delta S system is going to equal, in this case, 75.3 kilojoules per mole. And hopefully you've all been used to converting to Kelvin by now, since you won't be using Celsius much. What this is going to equal then is 373.15 Kelvin. You don't really need that 1.5. It shouldn't change my answer much here. What you end up getting is 0.2018 kilojoules per mole Kelvin. So that's the delta S of the system. Delta S of the surroundings then, you're just going to use this equation here. So delta H of the system is going to be the same, but for this one, you use the temperature of the surroundings. So what that's going to be, so delta S surroundings equals negative 75.3 kilojoules per mole over 68.9 plus 273.15 is going to be 342.05 Kelvin. And what that ends up giving you then is negative 0.22014 kilojoules per mole Kelvin. So you have those two values. To find the delta S of the universe, all you have to do is add those two values together. So delta S of the universe equals 0.2018 plus negative 0.22014, which equals, let's see, negative 0.0183 is what I got. And this is in kilojoules per mole Kelvin. That's the same thing as 18.3 joules per mole Kelvin. Sorry, negative 18.3 joules per mole Kelvin. And so you got a negative value. Remember, if the entropy change for the universe is negative, it's not going to be a spontaneous process. And if you think about it, that does make sense, because we're basically asking if water is going to boil at 68.9 degrees Celsius instead of 100 degrees Celsius. Since it's below that boiling point, it makes sense that it won't be spontaneous for that water to boil. So, but if it were over 100 degrees Celsius, we'd expect to see that the entropy change of the universe would be positive, just because it would end up being more favorable for that water to start boiling. So just an extra thing to think about. And once again, so this is like negative 18.3 joules per mole Kelvin. If I asked for you to find the entropy change when you vaporize, we'll do 18.02 grams at this temperature. All you have to do is convert that into moles. That would be 1 mole is 18.02 grams. And then, so you just have 1 mole times this value, and you get negative 18.3 joules per Kelvin. So whatever it does, if it gives you a mass, you can do this first step the exact same. And at the end, just multiply everything by the number of moles. You'd cancel out the moles and get the actual value of entropy for that certain amount. Okay, if there aren't any questions on that, I will move on to the next step then. And I guess actually for number 8, it's just a basic solubility question. Maybe a way you haven't thought about it for a while though, but I'll give you guys a second to see if you can figure out what the KSP value should be for that. So once again, just message me when you figure that out. Someone asked if we should use 273.15 or just 273. Either one works. So if you think about it, you're basically, for this answer, you would submit it to about 3 sig figs, and 273 and 273.15 would both have 3 sig figs as well. Like to 3 sig figs, I mean, would be the exact same. So because it's just off by like 0.15, when it's such a big number, it really shouldn't change your answer much. And it definitely wouldn't change it outside how the test is going to round. So either one works. If 273 is more normal for you, just use it. I use 273.15 because it's technically more accurate, but yeah, don't worry about doing the 0.15 if you're not used to that. For the answer to 8, by the way, your answer should be somewhere between 10 and 100. I'm going to tell you that. Getting a few right answers in, so nice job. Yep, everyone who's submitted an answer so far is right, so if you got it, nice. I'll give you guys about 30 more seconds to finish this up. And I'll work it through you. And number 9 then will probably take, I don't know, it'll definitely be the longest problem we've worked on just because titration seemed to take a while. Okay, cool. So yeah, every answer submitted was correct. Basically, all you have to think of for this is remember KSP is the equilibrium constant that goes with the reaction of this breaking up in solution. So the reaction there is going to be FeCl2, which is a solid. It's going to break up into Fe2 plus, which is aqueous, and 2Cl minus, which is also aqueous. So if you think about what the ice table would look like, initially you have 0 of both. For this, you're going to add S or X, whichever you use. This one, since there's a 2 in front of it, you're going to add 2S. And so equilibrium, you have S and 2S. What KSP equals then, remember, is going to be basically, since there's no reactants for this, it's just going to be the products times their coefficient powers. So times each other to their coefficient powers, I mean. So what you're going to have then is that KSP equals S times 2S in parentheses squared. So make sure you square that 2 as well. Well, this is going to then equal, we know the molar solubility is equal to S basically. So you can either, for these problems, solve for the molar solubility, which is the concentration that can be dissolved, or you can solve for KSP. For this one, it gave us the molar solubility. So that's going to be our S value we plug in. And we actually don't have the KSP. So we're just going to plug in 2.1 for S, plug this into our calculators and solve. So this is going to end up equaling, if you carry this out, it's going to equal 4S cubed actually, which equals 4 times 2.1 cubed, which ends up equaling 37.044. As I said, that's what most of you got. So this is one where you might not be used to solving for the KSP. You're probably more used to solving for this S value here, but all you'll have to do when you solve this is kind of just think about it a little backwards. It's the same process. When it gives you the solubility though, that's the S value that you're using. And if there aren't any questions on that, I will move on to the last one, which is the titration. So before I do this one thing I do want to point out, a shortcut for any titration problem. If you are at the halfway point to the equivalence point, the pH is just going to equal to pKa. So I'm going to write that down. So halfway to equivalence point. pH equals pKa, which remember the pKa is the negative log of the Ka, which is right here. But that is always going to be true no matter what. The reason for that is if you think about, I'll do the Henderson-Hasselbalch equation. If you have pH equals pKa plus log concentration of A minus over HA. At the halfway point, basically what's going to happen is, let's say you had 2 moles of A minus to start with and no moles of HA. At the halfway point, one of those moles of A minus will be converted. So you're going to end up having 1 mole left of A minus over 1 mole of this. Log of 1 is always going to be 0. So this term completely would go away. You're always going to just get that pH equals pKa. So this problem is not at halfway to the equivalence point, so it won't come in handy here. But definitely I'd recommend you remember that for the test, because you can just use that little shortcut if it ever asks you something involving halfway to the equivalence point. So remember, that's only halfway to the equivalence point, but there is that little shortcut there. But moving on to the actual problem. So it gives you 40 milliliters of 1.2 molar base. I did forget for this problem to label a couple things. We're going to say we're titrating with 1.0 molar HCl. That's very important for solving this. The other thing I wanted to clarify is that this Ka is the Ka of the conjugate acid, not of the weak base itself, because obviously a weak base is going to use a Kb value, not a Ka. And so I will give you guys a chance to figure this out. If anyone needs help getting started, once again, feel free to message me and I'd be happy to help. But you should, for this exam, be able to find the pH at the equivalence point and at any point before the equivalence point, including before you've added anything. But for this, we're just going to do 10 milliliters before the equivalence point and the equivalence point. So once again, feel free to message me if you have any questions. If not, I'll give you a couple minutes to work this out, and then I'll work it out for you. One other problem that I didn't make a practice problem of for this worksheet, but you will want to kind of refresh yourself on, is the polyprotic acids. Just make sure you know that for any of those, there are a couple shortcuts available with those that, I don't know. If you have questions after this, I can explain that in more detail. I don't want to throw you off or stop you guys from working, but that is another problem that you should be able to do. If not, I think most of the exam material should be covered with this worksheet. And as I said, definitely you'll want to look into Dr. Kautz's problems he's done in class. I think that's a really good place to start. And so I have had a couple questions about how to actually get started for this. So I will kind of get you started and then let you guys go from there. The first thing I'm going to do is actually figure out the volume needed to get to the equivalence point. And so to do that, the first thing I'm going to do is figure out how many moles of the weak base are present. And all I have to do for that is I'm going to convert the 40 milliliters into 0.04 liters. So we have 0.040 liters times 1.2 molar, which actually ends up giving you 0.048 moles of the weak base. That says weak. That's really bad handwriting. I apologize. So we have this many moles of the weak base. To figure out how many milliliters or liters of the acid we have to add to that, basically you're just going to then divide this by the concentration of the acid you're titrating with. So I'm going to divide that by 1.0 molar. That means that it's going to take 0.048 liters or 48 milliliters of HCl to get to the equivalence point. And so the first question then actually asks, what is the pH 10 milliliters before the equivalence point? So you do have to figure out what the equivalence point actually is before you can do that. We found out the equivalence point is at 0.048 liters. To figure out 10 milliliters before that, you're just going to subtract 10 from this. So the first part of the problem then is going to be the pH at 0.038 liters added, or 38 milliliters. And so hopefully that's enough for some of you to get started. If you're still stuck, just let me know and I can kind of work through it a little more. This part, remember, where you're in that buffer region before the equivalence point, I like to use the Henderson-Hasselbalch equation. You can use the other version as well if you're more familiar with that, whichever way you want. But yeah, I'll give you guys a second to work that out. If anyone's stuck, feel free to message me again. And this is where I like to use what I call starting stress, or before stress and new, for the number of moles. I did that kind of table, if that kind of is a little refresher if you're still stuck. So I'm not going to work out the whole thing, but I will kind of just write out some of the steps if you're still stuck. But what you're going to have is, if you think about the reaction taking place, you're going to have A minus turning into HA. You could write this as B minus, whatever it is. It's just a generic weak base. So that works for this. What I'm going to have is a before stress and new table. So before we've added anything, there was no acid present. And we calculated earlier that there were 0.048 moles of the weak base present. So this is 0.048. We're adding 38 milliliters, which we equated to be 38 moles. So 0.038 liters times 1 molar is just going to be 0.038 moles. So minus 0.038 here, plus 0.038 here. And that gives us 0.01 moles of this. And this is 0.038 moles of this. At this point, then, you could convert to concentrations. What I like to do is use the Henderson-Hasselbalch equation because it lets you use moles. And so all you have for this then is the pH is going to equal the pKa plus log concentration of A minus over HA. And I wrote that as concentration. The reason you can use moles then is that the volumes actually cancel out. So it's just going to be moles of A minus over moles of HA. And so I guess I'm this far, so I might as well work it out, the rest of it. So pH is going to equal negative log of the Ka. And the Ka from earlier is going to be 5.56 times 10 to the minus 8. Then plus the log of concentration of A minus is 0.01 now, over 0.038. And so if you're using the Henderson-Hasselbalch equation, I would definitely recommend you have that available with you if you like to use this method, just because it's a little more complex equation. But when you type that in your calculator, you should get a pH then of 6.675. So moving on to the next step then, I'll just finish working it out. Basically, at the equivalence point, remember what's happened is, if you look at this before stress new table, I'll just write that out again down here. That means, so you have A minus to HA again. I'm just going to write BSN for before stress new. We're just going to go back to the beginning. So before you added anything, you had 0 moles of this. And this would be 0.048 moles of this. So I had a question, I guess, for the previous step. If you convert to concentration, what would the total liters be? Great question. So basically at this point, the initial volume was 40 milliliters, and we said 10 milliliters before the equivalence point. We found out that would be 0.038 liters. So all you have to do to find the total volume at that point is add the two volumes. So 0.038 liters plus 40 milliliters is 0.04 liters. So that would be 0.078 liters for that concentration. Great question. Moving on to this second part then though. Basically, remember at the equivalence point, you're just gonna convert all of these to the other one. So this will be minus 0.048 moles. This will be plus 0.048 moles. That means that you have 0 left of the weak base. All of it is now the conjugated acid. So you have 0.048 moles of the conjugate acid. And at this point then, you can't use the Henderson-Hasselbalch equation just because all that's left is actually this weak acid. So this comes back to finding the pH of a weak acid. So you do have to find the concentration first, and to do that, it'll be similar to what I just said for the last one. We said at the equivalence point already that was going to be 0.048 liters. So in this case, to find the new volume, it's going to be 0.048 liters plus 0.04 liters, which was that original volume. So just this divided by 0.048 plus 0.04. And that gives you a concentration of, let's see, 0.5454 basically. So that'll repeat, but basically this is what you're going to get as the new concentration of that weak acid. All you have to do then is do an ice table, and you'll get to hopefully the correct answer. That should give you, if you think about it now, you do have a weak acid. So it'll give you the concentration of H3O plus, and then you can solve for the pH. So I'll give you guys a few more minutes before I actually show the answer to this one. If you can message me that just to see that you guys are on track. If not, this is the last problem I had planned. If anyone wants to stick around and ask any more questions, I technically am in office hours now till 12:30. So feel free to stick around. Also, if you do have any other questions that come up, feel free to email me. It might make sense to schedule a Zoom appointment tomorrow at some point. I do have my office hour from 11 to 12:30 tomorrow. So I'd be happy to meet with you then. But if that time doesn't work for you for some reason, just let me know. And I don't think we're allowed to meet with you guys after 4, which makes sense because that's when the test starts. But basically, yeah. So if you have any questions, just feel free to message me and we can set up an appointment. Okay, so I will go back then and explain how to do the pH before the equivalence point without the Henderson-Hasselbalch equation. So I will kind of just work through that again. So let me, just gonna move this part actually. Move that down there. Okay. So what you would do at this point, you should have still figured out these new numbers of moles here. So you should get 0.01 moles of the A minus, 0.038 moles of the HA. We said that, so we're in moles right now, you do have to find the concentration at this point. To find the concentration, all you'll do is divide the number of moles by the total volume. The total volume is going to be the original volume, which was 0.04 liters, plus how much we've added, which is now 0.038 liters, for a total of 0.078 liters. So to find the concentration of A minus, that's going to equal 0.01 moles over 0.078 liters. To find the concentration of HA, once again, this value just comes from that table. The moles of HA also comes from that table, which is 0.038. Over 0.078 liters once again. So I do need to plug this in my calculator really quick. So this gives you a concentration of A minus of 0.1282 molar. For the HA, you're going to divide that by, so 0.038 by 0.078, which gives you 0.48, don't know what happened there, 487 molar. So those are the two concentrations you're going to work with. At this point then, you actually don't need to use an ice table or anything. The easiest way to do it is actually set up what Ka equals. So remember, Ka equals the concentration of H3O plus times the concentration of A minus over the concentration of HA. And so at this point, we know the concentration of HA and A minus, and we know Ka because that was given to us in the problem. What we'll solve for here then is the concentration of H3O plus. So what we get for this then is, what is it, 5.556? Yeah. So 5.56 times 10 to the minus 8th equals the concentration of H3O plus times A minus is 0.1282. Over 0.487. Solving for this then in your calculator, let me just figure out what this actually is. And that should give you that H3O plus concentration equals, I believe, 2.112 times 10 to the minus 7. The pH then is just going to be a negative log of that, which equals 6.675. Which, if you notice, is the exact same answer we got the other way too. So both ways work. That's just the way you can check it. Does that make more sense? Okay, cool. So I am just going to solve that second problem then, or the second step of this, and then that'll be it. So we figured out now the concentration of HA. Remember, there's no A minus left at this point, because at the equivalence point, all of the A minus has been turned into HA. So for this, I am going to use an ice table just because you do actually have to solve for X. So at the equivalence point, you do need an ice table. Before you've added anything, you need an ice table. In that buffer region, you don't have to worry about the ice table step. You can jump right into Henderson-Hasselbalch or that other equation. So looking at this then, we have this concentration. If you think about what's happening, you have HA plus H2O goes to H3O plus A minus. You don't need to worry about water. This initial is going to be 0.5454. There's none of this yet, and because we're at the equivalence point, there's none of this left. So this is going to be minus X plus X plus X. So at the equivalence point, we have 0.5454 minus X, X and X. So all you have to do then, is you have that the Ka equals X squared over 0.5454 minus X. And the Ka, remember, was given to us as, I believe, 5.56 times 10 to the minus 8th. Yep. So all you're going to do then is use your solver function again, plug this in, you should get an x value. The x value you get should be, assuming I did this right earlier, is 1.74 times 10 to the minus 4th. Thinking about what x represents, for this problem, x does represent the concentration of H3O plus. So this is going to equal the concentration of H3O plus. To find the pH, you just take the negative log of this. And so that means the pH you should get equals 3.76, which some of you had messaged me already. So if you got that, nice job. And so, yeah, that's all I have. As I said, I'll be around for another 5 or 6 minutes if anyone has any more questions. If not, good luck on your test tomorrow, and feel free to email me any questions you have. Definitely look over the review worksheets that Dr. Kaups went over in class. This should be a good resource, anything I've done in Reci, and yeah. And I can scroll up to question 8 so someone can look at that. There you go. For those of you that are left, do you have any questions? You want me to scroll up? Just let me know in the chat, I suppose. Oh yeah, I can talk about polyprotic acids. So for polyprotic acids, I'll just scroll down here. I'm gonna make up an acid. So let's say, I don't know, we'll just call it H2A. And we'll say that it has a Ka1 that equals, I don't know, we'll do 1.2 times 10 to the minus 3rd. We'll make Ka2 equal 2.8 times 10 to the minus 8th. And so basically when it comes to polyprotic acids, one way you could do it is by working through 2 complete ice tables. So you'll work through the first one, figure out a concentration of H3O plus, use that for the second ice table, and use that for the second dissociation. Definitely, I would not recommend doing that because that takes a lot of time. The whole key with polyprotic acids is basically when you want to find out the pH, all you'll have to do is use whatever pH you get from the first ice table using this. The reason for that is whatever happens here when you add some H3O plus, it's going to be such a small number that it's never going to change it, at least in this class. And like other classes, or if you need to be really precise, it would. But basically what you can assume is if you have a polyprotic acid, just find the pH using that first Ka. So what I mean by that is you'd have that equation. So H2A plus H2O gives you HA minus plus H3O plus. What you do then is you'd start off with whatever concentration you have here. We'll say the concentration of 1 molar just for the purpose of this. You have none of either of these. Don't use water. So at equilibrium, you have 1.0 minus x, x, and x. Whatever you solve for using that first Ka value, so using the one that has the box around it, this will give you a concentration of H3O plus that you start with. all you have to do is take the negative log of that. That will give you the pH. So literally all you have to do is solve for the first, using that first Ka, that will give you the pH. The other question that it could possibly ask you about polyprotic acids is actually another shortcut. Let's say it asks for the total concentration of A- in solution, or A2-, I guess. So if it wants to find the concentration of A2-, what that means is it's lost both of these protons. So you want to use this value here. And all you're going to do is the concentration of A2- is going to equal that Ka value. So in this case, the concentration of A2- equals 2.8 times 10 to the -8. And those are basically the only two shortcuts I really think you should worry about for this. As I said, so literally the pH of a diprotic acid is going to be the exact same thing as if you use that Ka1 and found the pH of a monoprotic acid, or what you're used to. So that is going to be it for finding the pH. So I'll write used for pH. Ka2 then is going to equal the concentration of A- or A2- in this case at equilibrium. And that's basically all you really have to worry about. But those are really handy shortcuts that could definitely save you a lot of time on the test. As I said, if you wanted, you could solve for X here. That would give you a concentration of H3O plus. Then you could plug that in and do a second ice table. Really don't worry about that. Literally, this will give you all the answers you would need to know for any type of question like that. And yeah, that's about it. Does that make sense? Or if you have more questions on that, I could, I guess, actually solve for this pH for you. Let's see. Yep. I can show you number 9. Before the equivalence point, let's see, where's that work? Hopefully this isn't too small. But yeah, so this is all of number 9 before that point. Except for that part. You have anything else, Milena? If not, I'm probably going to shut it down. Oh, pH. For which part? Oh, for that previous problem? Yeah, I can actually solve it for you, and then that'll be good. So what we'd have here then, let's see, we have x squared over 1 minus x equals 1.2 times 10 to the -3rd. Let me just plug that in my calculator really quick, and I'll let you know. You said, yeah, I got 1.5, but yeah, 1.47 is probably close enough. Yeah, so I just solved for this. As I said, put it in my calculator. I got 1.508, 1.47 is probably just a rounding thing. So yeah, does that make sense? Yep, cool. See ya and good luck.